Right, lecture 24, continuous versus discrete random variables. Really, I'm just going to do a few examples here to compare a continuous random variable with a discrete random variable, computing probabilities thereof. So I say in the notes here, let's suppose that x is a continuous uniform random variable that can take on any real number value between 1 and 9. And let's suppose that y is a discrete uniform random variable that can take on any whole number value between 1 and 9. Well, first off, the interesting thing here is I'm not talking about a experiment, a random experiment that has numerical outcomes that give you these random variables. I'm just saying, let's suppose we have these random variables, and I just give you the specifications for them. All right, we're going to find that that will happen occasionally. It'll be useful for us to be able to just think a little bit more abstractly about random variables and not always attach them to the numerical outcome of an experiment, although we could come up with an example of an experiment. I mean, maybe for the discrete one, you've got a 9-sided die, right, or something like that with the numbers 1 through 9. But let's not really worry about that. Let's just think about the, what I say first is the probability density function, PDF, of x is, and I say pause me and try to draw it. All right, so please give me a pause and read what we have. It can take on any real value number between 1 and 9. Can you write the probability density function? Draw the graph. And if you've paused me and tried, I hope you get something like this. We have, if you notice, that it can only take on values starting at 1 and going all the way over to 9. And it's uniform, which means that's the same level all the way across, right? The area is the same all the way across. The height, I should say, is the same all the way across. And what is that height? Well, in order for the total area to be 1, it is, look, the length is 9 minus 1, correct? So the length is 8. The height has to be 1/8 so that the area is 1. Okay, I hope you can get that. Let's see, the probability histogram for y looks a little bit similar, but there are differences. So pause me and try to do the histogram for y if you can. Okay, let me come over here, I think, and we'll look at that. It can take on any whole number between 1 through 9, inclusive. So what I have is I have the histogram bar above 1, where are we? 1, and then 2, and then 3, etc., all the way up to 9. I have a total of 9 of them. It's uniform again, which means they all have the same probability. What does that probability have to be? Well, I can actually think in terms of area again because the widths of the bars are 1, but really I want to just think that I have 9 total values. Probability is equal. If it's got to be a total of probability of 1, as it has to always be, the height has to be 1/9. All right? All right, and I make a little comment here before we go on that if I go back, we have here the PDF of the probability density function for x, which tells me not the probability for a value of x, correct? Because the probability for a value of x is 0. But this is a curve up here. It's a straight line, a flat curve. But it gives me the ability to compute probabilities related to x. And of course, we know that we're going to compute probabilities of x being in some interval, is what we generally do with that. And that's what I'm saying in that paragraph. Well, over here, I have a function, really, that gives me the actual probability value at the various points, 1, 2, 3, 4, 5, 6, 7, 8, 9, because this is also called a probability density function, but it's just that there is actual probability concentrated at each numerical value. There are only 9 possible ones. The probability is 1/9 at each one. And in the case of the continuous random variable, it's 0 everywhere, but we get probabilities by looking at areas. Okay, so with that in mind, I want to work a few examples, and let me just put them, let's see, I think I have both of them up here. Yes, all right, so look at number 1. Number 1 says, find the probability that x is greater than 3, and find the probability that y is greater than 3. So please pause me and see if you can do those. What I will do, and I want you to do, is to try to draw in what that probability is in terms of areas or in terms of bars on the histogram, and then compute it. So give me a pause and try to do those two. Okay. I want the probability that x is greater than 3. So I really want the area, if I can get it on the map here. This is really funny to draw. Okay, I'm going to start at 3, and I'm going to go up to my horizontal bar, and I'm going to go all the way over to 9 and go up, and I want this area, right? And the area, the probability that, oops, I'm writing on my numbers there, aren't I? Let me see, maybe I'll do it right here. The probability that, if I can get my head out of the way, that x is greater than 3 is, what's the area? The height is 1/8 times, what's the width? It's 9 minus 3, right? 9 minus 3, so that's 6/8 or 3/4 or 0.75. Okay, what's the probability over here that y is greater than 3? Well, if it's greater than 3, I cannot have the value 3, so I have to jump all the way over to the value 4. I can have that, and 5, and 6, and 7, and 8, and 9, right? So it's the probability that y equals 4, or 5, or 6, or 7, or 8, or 9, which is 1/9 plus 1/9 plus 1/9 plus 1/9 plus 1/9. Let's see, 4, 5, 6, 7, 8 plus 1/9, and that's 1, 2, 3, 4, 5, 6. That's 6/9, which is 0.66666 forever, right? So it's 2/3 is what that becomes. Okay, so that's number 1. Very different answers, right? Even though the random variables seem like they might be the same, they're not. Right? They seem similar. They take on values from 1 to 9, but one's continuous, one's discrete, and we get very different answers for probabilities. And that's the way it's going to be all the way down the line here. And that's really what I want to emphasize on each of these. Okay, so the next one is I want the probability that 2 is less than or equal to x, which is less than or equal to 7. So I come over here and I look at x value has to be between 2 and 7, right? So right here, on up, and over to here, on up, right? So I get that area. So it's, again, 1/8, because that's the height, times 7 minus 2. That's 5/8 or 0.625. Okay. Over here, what's the probability that 2 is less than or equal to y is less than or equal to 7? It's the same problem, right? Yes. Well, that means y could be 2, or it could be 7, or it could be anything in between. So the answer is, I come down here, it's got to be that one, or 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 that one, right? So it's 1/9 plus 1/9 plus 1/9 plus 1/9. This is 2, 3, 4, 5 plus 1/9 plus 1/9, 6 and 7. And again, I guess you get 6/9, which is 2/3 or 0.6666 forever. Okay, again, different answers. I grab the two end values and I get everything in between. Let's contrast this with number 3. Number 3 says the probability that 2 is less than x and less than 7. So let me just kind of cheat here a little. It's the probability that 2 is less than x and x is less than 7. What's the difference here? Because I have here a continuous random variable, all I've done is I've plucked off the possible values of 2 and 7, each of which for a continuous random variable has probability 0. So I've not done anything. I have exactly the same problem. It's the area between these two values. So the answer is exactly the same. I don't have any more work to do. Whether I'm including those endpoints or not for a continuous random variable doesn't matter because I get the area between. You know, whether I can include the value right at 2, the area of this line is 0, or right at 7, the area is 0. There's no difference. Over here, let me again kind of cheat here. Probability that 2 is less than y and y is less than 7. That means I can't have 2 because 2 has to be less than y, so I can only have 3, 4, 5, 6, and has to be less than 7, so I can't get 7. So basically, I take away the first 1/9, and the last 1/9, right? And that leaves me with 4/9. So the probability there is 0.4444 forever. The bar above means the digit goes on forever, right? Okay, so big difference, right? I actually yanked off the values at 2 and 7, and that made a difference because the random variable is discrete. It actually has probabilities, non-zero probabilities at those endpoints. So if I throw them away, they're gone, and it makes a difference. Over here, it made no difference. All right, let's see. I think I have one more. So let me rub this out. Okay, it says, number 4, it says, I want the probability that 2.2 is less than x, which is less than 6.8. Okay, I look down here, my continuous random variable, since I can take on any value between 1 and 9, I go find my 2.2, which is probably about right there, and I want to do that is my left bar for my rectangle, and 6.8 is going to be about right there. So I'm going to get this area, and of course that's 1/8. The height hasn't changed, and it's now 6.8 minus 2.2, so that's 1/8 times 4.6, which I think is 0.575. All right, so there's the probability there. Let's come over here and do the analogous thing for the discrete random variable and see what that does for us. See how we have to be careful in our thinking. All right, so I want the probability that 2.2 is less than y, which is less than 6.8. So if 2.2 is less than y, I can't go, whereas 2.2 is about right there. It has to be less than y. I can't get any of this bar. I either get all or none of it, but I have to be the random variable y, or sorry, 2.2 has to be less than the random variable y. So I have to jump over to the value of 3, correct? Because over here it's the value 2, and 2 would not be less than 2.2. So I can only get 3, and then I can go 4 and 5, and I got to stay less than 6.8, so I can go up to 6, but I can't go to 7. So I think I get 1/9. That's for y being 3, and for 4 I get 1/9, and for 5 I get 1/9, and for 6 I get 1/9. Right? 3, 4, 5, and 6. So again I get 4/9. So I get 0.4444 forever. Okay, I hope you can see how to compute probabilities for discrete versus continuous random variables, and this will help us in terms of thinking, especially when we start thinking about continuous random variables and probability being area, which you've already been doing, but we're going to do a lot of that in the next few lectures. So I hope this has kind of clarified a few things for you.